All right, maybe it's time to start. So welcome everyone to the Oxford Lectures on the Philosophy of Mathematics. I'm Joel David Hamkins, and today's lecture is on the Gödel incompleteness theorems and related matters. So I think it should be a lot of fun. We're going to see several different proofs of the incompleteness theorem, and I'll try to put things in context for you. So really, the way I think about it is that mathematical logic as a subject really came of age with the Gödel incompleteness theorems. And those theorems show that for any sufficiently strong formal system in mathematics, there will be true statements that are not provable. And furthermore, in particular, the consistency of such theories is one of those true statements that's not provable. So the theorems are really technically sophisticated, involving some sophisticated mathematics, but they're also at the same time engaged with what I view as deeply philosophical issues and concerning the fundamental nature and limitations of mathematical reasoning. And this fusion of mathematical sophistication and philosophical concern has really become characteristic of the subject of mathematical logic, and really one of the great pleasures of the subject as far as I can view it. So the incompleteness theorem is now a core consideration in any serious discussion of the foundations of mathematics. They must engage with the incompleteness theorem. Okay, so to put it in context, though, let's imagine sort of prior to Gödel, what would be our hopes and dreams for the philosophy of mathematics? If we put ourselves back in the early part of the 20th century, of course, by then the axiomatic method had been firmly established and enormously successful in many different fields, particularly real analysis and other subjects. And so this formal axiomatic method had been gaining steam, and maybe one would want to complete the process. Of course, if one has a weak theory, that might be statements you can't prove in the weaker theories, but you make a stronger theory and then you can prove more, and maybe one can find the one true final theory that is going to settle all the statements of mathematics and answer every single question. So I view that as a very natural goal in the context of sort of gradually developing axiomatic method. Okay, another issue though at that time in the early 20th century were these troubling antinomies or contradictions. Of course, the word antinomy is just a polite way of saying contradiction. They had found these contradictions in some of the fundamental mathematical theories, particularly in the naive account of set theory. So for example, Russell had refuted Frege's system with the Russell paradox, and there were other paradoxes, the Burali-Forti paradox, and so on. And so that's rather troubling if one is viewing those systems as trying to fulfill the first goal that we had mentioned of this completeness. And so so what maybe we would be seeking a sort of unified foundation for mathematics, which could answer all the questions, but also we would want to feel secure in that foundation by having maybe a consistency proof of the consistency of that formal system. I mean, how intolerable it would be if we were to discover later that our fundamental axioms were simply inconsistent. Okay, so there's really two prongs to this goal, and this has become known as the Hilbert program. These were the hopes and goals of the Hilbert program. So there were two aspects to it. Namely, first of all, we want to have a complete theory, and that theory might be a kind of infinitary theory. Maybe one imagines something like set theory, on which we're going to answer all the mathematical questions, but then we want to feel secure about that theory by maybe purely finitary reasoning. We want to argue that that theory is consistent. So at Hilbert's retirement address in 1930, he said, "Wir müssen wissen, wir werden wissen." So we must know, we will know. And this is, I interpret, a way of saying that he hoped to answer mathematical questions. It's an aspiration to completeness of the mathematical theory. We want to give a mathematical theory that will tell us the answers to any given question. So we want our best mathematical theories ultimately to answer all of the troubling questions. And regarding the second role, Hilbert explained how he imagined maybe it might go, that we would have this finitary proof of the sort of safety of the infinitary theory. And this leads one to the view that's become known as formalism. So So the idea is that we should view the mathematical process of reasoning from a theory, of making deductions from a theory, as a kind of formal mathematical game, right? We're manipulating these symbols and following the rules, say, of the proof system, making more deductions from them, and so on. And one needn't encumber the mathematical ontology with those uncountable or even infinite sets just because the assertions speak of them. If we just look at the assertions as finite sequence of symbols, then it becomes a kind of finitary process, divorcing the assertions themselves from the meaning that maybe one might have wanted to attribute to them. So we have basically these finite sequence of symbols that we're manipulating according to the rules of the deduction system. And this is a philosophical position known as formalism. So the view, according to formalism, is that mathematical assertions really have no meaning at all. There are no mathematical objects that they are speaking about, no uncountable sets and no infinite functions. So according to the formalists, the mathematical assertions we make are not about anything. Rather, they're just meaningless strings of symbols that we're manipulating according to certain rules. Okay, so Hilbert has these two goals: the complete axiomatization of mathematics, sort of the higher theory is going to be complete, and then we want a finitary proof that that theory is consistent, and that finitary proof is going to be using these ideas of formalism. We're going to prove that those rules, that mathematical game of reasoning in that upper theory, it will never lead us into contradiction. This is what we want in the Hilbert program. Okay, so in that way, we can maybe regain some trust in the infinitary theory. If we had such a proof on finitary grounds that the infinitary theory would never lead us to contradiction, then maybe that would give you some reason to have some confidence in the conclusions that you're making on that theory, even if you don't stick with the formalist interpretation. Okay, so let me set up now kind of two imaginary worlds. Let's imagine that Hilbert was right. So let's imagine what would life be like in Hilbert's world. So suppose that we did have this theory that was complete and that we could prove it's consistent. So, well, if we had this complete theory, we could write down the axioms of a complete theory, then we could imagine systematically undertaking all possible deductions from those axioms in that complete theory. And in this way, we could systematically generate all the theorems of that system. And that would include all and only the true statements of mathematics. I mean, if Hilbert was right, then we would have this complete axiomatization of true mathematical statements. And so by simply applying the formal deductive rules to that system, we would be able to enumerate a list of all and only the true statements of mathematics. And so we could basically churn out mathematical truths by a rote procedure. And that would be the fundamental nature of mathematics, maybe. To prove a theorem would simply be to turn that crank of the theorem enumeration machine to just systematically generate all possible theorems. If you had a mathematical question, you could just wait for either that statement to get tossed out of the machine, or to be produced by the machine, or the negation of that statement to be produced by the machine. Okay, what's the alternative? If Hilbert is wrong, then maybe there is no complete axiomatization. And furthermore, maybe we're not able even for any given axiomatization to prove that it's consistent even. And so in that situation, we would always have some doubt about whether our theory was right. And also we would be beset with sort of creative choices about what new axioms to add. And that would be a fundamentally non-mathematical activity of deciding how to extend a given theory, because we wouldn't be able to prove the new axioms. I mean, it's not complete. So there's some statements that it neither proves nor refutes. And we would have to decide which one do we think is true and on what basis would we make such a decision. Okay, so this is a fundamentally different picture of the nature of mathematics if Hilbert is wrong. Now that maybe the next thing to say is that Gödel's incompleteness theorems are basically like bombs exploding at the very center of the Hilbert program, decisively refuting the whole idea of the Hilbert program. So the incompleteness theorems show, first of all, that we cannot, in principle, ever enumerate a theory that's complete. Okay, we can't enumerate a theory that's going to prove all and only the true statements of mathematics, and furthermore, we can't even prove in a finitary theory the consistency of that theory, let alone the consistency of a much stronger infinitary theory. That's the first incompleteness theorem and the second incompleteness theorem. So we'll talk about this in detail, but one should basically understand the incompleteness theorems as a decisive refutation of the Hilbert program. So let's talk specifically about the first incompleteness theorem. And I'm going to give you several different arguments. But there's a lot of different ways to prove it. So let me give you a form of the first incompleteness theorem. I'm going to talk about the statement that says, there's no computably enumerable list of axioms that prove all and only the true statements of elementary mathematics. Well, okay, what do I mean by elementary mathematics? I mean a theory that's capable of expressing and formalizing finite combinatorial reasoning. Okay. Now it turns out, in fact, we'll talk later, that just the ordinary theory of arithmetic is capable of doing that through the process of arithmetization. But for now, let's stay a little bit informal about it. And so by the true statements of elementary mathematics, I mean the statements about finite combinatorial reasoning, about sort of graph coloring and maybe Turing machine operation and things like of this nature. So the first incompleteness theorem says there's no computably enumerable list of axioms that prove all and only the true statements of elementary mathematics. So let's give a proof of that. These different proofs are qualitatively different, but I want to give a proof of this version of the theorem that's essentially due to Turing, to Alan Turing. So it was proved after Gödel proved his theorem by other means. Suppose that we had such a theory. Okay, suppose we had a computable list of axioms that proved all and only the true statements of elementary mathematics. So now, by applying all possible deduction rules to those axioms, we can systematically generate all of the theorems of that theory. So therefore, we would be able to enumerate all and only the true statements of elementary mathematics. Not just the axioms for it, but the truths themselves. And now Turing argues, well, if we had such a theory, then we could solve the halting problem. Because given any Turing machine program, we formulate the statement that that program halts on input 0, say. That would be a statement of elementary mathematics. And we would look and see if that statement shows up on the enumeration, or if the negation of that statement shows up on the enumeration. And one of them would have to, because we said that that enumeration was all and only the true statement. So either the program does halt or it doesn't, and whichever one it is going to show up on the list. And so we just wait until one of them shows up, and when it does, then we say, yaha, it halts, or aha, it doesn't halt, because that was what the list told us. So therefore, if there were such a complete enumerable list of axioms, then we would be able to computably solve the halting problem. But we proved last week that there is no computable procedure for solving the halting problem, and therefore that's a contradiction. So therefore, there cannot be any such list. Okay, this is an argument that's basically showing the Gödel incompleteness theorem is essentially similar to the undecidability of the halting problem, because if you had such a list of axioms, you could solve the halting problem, but you can't solve the halting problem, so therefore you can't have such a complete axiomatization. Okay, so the proof actually shows something a little bit stronger than what I said. Namely, it shows that if you have a theory, T, if you have a true theory for part of elementary mathematics, and it's computably axiomatizable, then there must be some Turing machine program that doesn't halt on a given input, but your theory can't prove it. Because if your theory could prove all such instances, imagine that whenever a program doesn't halt, your theory proves it. Then we could solve the halting problem, because given any Turing machine program and input, during the day, I run the program on the input and I try to see if it's going to halt. And at night, I look for a proof in your system that it won't halt. And if your theory proved all the non-halting instances, then look, either the program does halt, in which case during the day I'm going to observe that it halts, or else it doesn't halt, in which case under the assumption we made on your theory, I'm going to find the proof that it doesn't halt. And so therefore I would be able to solve the halting problem. Okay, but I can't solve the halting problem, as we proved last week, and as Turing proved in 1936. And therefore, there must be some program that doesn't halt, but your theory doesn't prove it. Okay, so that's a true statement that's not provable in your theory. So let's turn to what's called the Entscheidungsproblem. So this was actually part of the title of Turing's paper. So the problem was put forth by Hilbert and Ackermann in 1928. This is before Gödel's theorem. And it's the decision problem of deciding whether a given assertion is logically valid. So given a statement in some first order language, we want to decide, is that statement true in all models? Is it logically valid? And Hilbert and Ackermann asked, is this a computably decidable problem? Well, actually, they asked, what is the algorithm to decide it? Because at that time, it was before Turing, and maybe the ideas of what it means to be computably decidable were not clear. And so part of the problem, really, in order to answer the question, you have to, first of all, develop a theory of computability in order to say that it isn't computably decidable. So it seems quite clear that Hilbert had expected a positive result. So he wasn't asking, is it computably decidable? He was asking, what is the algorithm to decide this? Okay, so maybe one can imagine what a positive solution to the Entscheidungsproblem would look like. Namely, it would be a particular algorithm, like you look at this and that and so on, and then you prove that that algorithm gives the right answer. But what's not so clear maybe at that time was, what would a negative answer look like? A negative answer would be a proof that there's no computable procedure for deciding whether a given statement is logically valid. And in order to make such a kind of statement, you have to have a clear idea of what counts as a computable procedure. And that's why it could really only be proved after the development of computability ideas, such as Turing's or Post's or Klee's, or Church's, I should say. Okay, so let's put the Entscheidungsproblem. Entscheidungsproblem is just German for decision problem. And at that time, it was the main decision problem, perhaps the only one. But there's many other decision problems that we have now. There's thousands of decision problems. I mean, complexity theory is full of decision problems. But let me mention another that are related to the validity problem. So when someone says the Entscheidungsproblem, they're talking about that validity problem of Hilbert and Ackermann. But we also have the, say, provability problem. Given a statement and a theory, is that statement provable in the theory? That's the provability problem. Or the satisfiability problem, given a first order statement, is it true in some model? Or the logical equivalence problem, given two statements, are they logically equivalent or not? And so one wants to know, well, how are these problems related to each other? And are any of them computably decidable, or are they equivalent in some sense? And indeed they are. So Turing, using Turing's ideas, one can show that all of those problems are Turing equivalent and reducible to one another. So let me just explain a little bit about that. Of course, the validity problem is the same as the provability problem because of the completeness theorem, right? A theory proves a statement just in case it logically entails this statement. That's exactly the completeness theorem, which was known earlier. And so the provability problem and the validity problem are essentially identical problems because of that. So let's reduce, say, the validity problem to logical equivalence. Suppose you have a statement and you want to know, is it logically valid? Well, all you have to do is take some other statement that you know is logically valid and then ask, are they logically equivalent? Because of course, the first one is logically valid just in case it's equivalent to something that you know is logically valid and not otherwise. So therefore, we reduce validity to logical equivalence. Okay, and conversely, we can reduce equivalence to validity because two things are equivalent just in case the biconditional statement is logically valid. So those problems are sort of equally hard. If we can answer one of them, we can answer the other. And similarly, if you can answer satisfiability, then you can answer questions about consistency or provability and so on. They're all Turing reducible to one another. That doesn't say yet whether any of them is undecidable or not. But in fact, all of them are undecidable and all of them are equivalent to the halting problem. Okay, let's prove that. So this is maybe how Turing argued in his 36 paper. Given a Turing machine program and input, what we want to do is write down a theory that formalizes the operation of Turing machines. So it's capable of talking about the states of the machine, and there should be an underlying order of each snapshot of the machine, what's on the head and what's on the tape and so on, and the relation between a particular cell at one stage and the next stage and so on. And so we can write down a theory that formalizes how Turing machines work. And then we could formulate the statement that P halts on this input. That would be a formal statement in that formal system that we created specifically for the purpose. Okay, so then if the program does halt on the input, then it would be logically valid that any model of our theory that's formalizing the notion of Turing machines would show that the program would have to halt. And if the program didn't halt on the input, then it wouldn't be valid, because we could take a sort of the intended interpretation of our formal system and produce a model in which the program didn't halt on that model, because the stages of time proceeded without end and so on, and at no stage did it ever give a signal a halt. And so therefore, if we could answer validity, then we could solve the halting problem, because I just described how to reduce a question about halting to a question about a certain statement being valid in a certain system. So therefore, we cannot answer the question of validity computably, because if we could solve the halting problem, which we cannot. Okay, so in each of these cases, we're showing that there's no computable procedure for answering these decision problems because we reduce the halting problem to them. Okay, so let me mention another version of the incompleteness theorem. It only came much later, decades later, but it's quite striking in my opinion. So the theorem says, for any computably axiomatized true theory of arithmetic, so if you have some theory of arithmetic that we're talking about, then you can write down a polynomial with integer coefficients in several variables. Okay, so for every theory, there's a polynomial you can write down. Maybe it fills half a page or something. These polynomials are quite gigantic, but still, you can write it down actually. For any computably axiomatized true theory of arithmetic, there's a polynomial with integer coefficients such that the question of whether it has a solution in the integers is not provable in the theory. So in fact, it has no solution in the integers, but this is not provable in the theory. Okay. So let me say it again. For every theory, there's a polynomial you can write down which doesn't have any solutions in the integers, but the theory does not prove that. So that's a true statement that's not provable in the theory. So therefore, it's a version of the incompleteness theorem. But it's just about these polynomials and whether they have integer solutions or not. It seems so sort of primitive. Of course, if we have a polynomial that doesn't have a solution in the integers, maybe you would expect to be able to prove that, but you can't prove all instances of it. So this is called the mrdp theorem. It's named for Matyasiewicz, Robinson, Davis, and Putnam, who proved it. And that theorem really answered one of the famous Hilbert problems. So at the beginning of the 20th century, Hilbert had this list of problems that were sort of intended to guide research for the coming century. And this was Hilbert's 10th problem. And again, he had asked, he wanted to know, what is the algorithm for solving a Diophantine equation? So given a polynomial, then answer yes or no, whether it has a solution in the integers. And the theorem is that there is no such algorithm. So again, Hilbert had asked, what is the algorithm? But in fact, the answer was, there is no algorithm, no computable algorithm for doing that. And the reason is, again, because if you had an algorithm for doing that, you could solve the halting problem. And a consequence of it is this non-provability version of the incompleteness theorem, having to do with those polynomials. Okay, so let's move on to the topic of what's called arithmetization. So if we think about the structure of the natural numbers with just addition and multiplication. So there's a formal language of arithmetic, the natural numbers with addition and multiplication. And maybe we have constants for 0 and 1, and maybe we have the less than relation, but actually it's definable from addition anyways. So this is called the standard language of arithmetic. And one of Gödel's key insights was that this language suffices actually to formalize essentially all finite combinatorial mathematical reasoning. And this is what's known as arithmetization. So to my way of thinking, arithmetization is one of these truly profound ideas. So it's a phenomenon that happens again and again, a profound idea that that has become mundane through familiarity. So we've become so familiar with what I view as instances of arithmetization now that it's simply no longer surprising that that we can do this arithmetization process. So let me explain this. So arithmetization is the idea that essentially any finite mathematical structure can be encoded in numbers, in the natural numbers. So we can have a number that's coding an entire structure. But this is obvious because all of us have computers at home that we write our papers in. Maybe you're writing in Microsoft Word or something, or maybe using some other editor, and you're writing your great novel into the computer. And of course, you conceive of the novel as having chapters and paragraphs, or maybe there's some of those paragraphs are quotations, so they're indented, or maybe they're in a special font or something like that. So we have a sort of higher level understanding of what you're creating. But ultimately, I think we all recognize that inside the computer, every single character in your document is represented, say, in ASCII or Unicode or something by a number. The ASCII system has 256 different symbols in the chart. You can look it up. Most computers are using Unicode, which has way more symbols, but the idea is the same, namely that every character in your document gets translated into a number. Maybe it's a ASCII was 256, which is 2 to the 8, so 8 bits of information. So every character is a number between 0 and 255. And then maybe some of the ASCII codes are interpreted as like switch to italic font or whatever. So there's the control characters in your document. But ultimately, the novel that you're writing in your computer gets translated inside the computer to this sequence of numbers. And each of those numbers can be written in binary as a sequence of zeros and ones. And so ultimately, the entire novel is just this really long, gigantic sequence of zeros and ones inside the computer. And 0 is indicated maybe with a low voltage, and 1 with a high voltage inside some transistor or something, or in the alignment of magnetic particles, on the hard disk, if you have a hard disk. And so these zeros and ones are represented somehow inside the machine. But the point is that the entire document is just an enormous number, and that might be called the Gödel code of your document. Okay, so we're all completely familiar with this process by which things that we create, and anything that you could write or describe, engineering schemata, anything that you could create on the computer is ultimately represented inside the computer by those kind of ASCII numbers, which are put together to make just one gigantic number inside the computer. And we know that if you make changes, or you cut and paste, or you do some process on the objects that are represented. Maybe you have a computer program that's representing finite graphs and you're applying some automorphism to those graphs. But ultimately inside the computer, that's just doing operations on those binary encodings. And ultimately those transformations are just arithmetic transformations. In fact, the most fundamental thing going on inside the computer are these logic gates, NAND and NOR and so on. And those can be viewed as arithmetic operations on the zeros and ones. And so in this way, any kind of finite combinatorial reasoning that could be represented on the computer at all, we know can be reduced to these kind of very primitive operations on the numbers. Okay, so this is arithmetization, representing mathematical structures with numbers in such a way that the mathematical operations that you might be doing to those structures are ultimately expressible in arithmetic. And now Gödel's idea was, well, because mathematical statements, okay, in arithmetic, the mathematical statements are talking about numbers, but the numbers can be representing mathematical statements, because of course we can apply the process of arithmetization to the formal language of arithmetic itself. What is a statement in a language of arithmetic? Well, it's a sequence of symbols with brackets and and signs and so on, and plus and times and quantifiers and so on. But that's just something that could in principle be represented with a Gödel code, using ASCII or whatever kind of coding you want. And so ultimately it's coded by a number, and this set of syntactic operations of things that you might do with such a symbol, like looking at its parse tree or looking at a proof and what step of reasoning was used at this step in the proof and so on. All of those things are subject to the process of arithmetization. And so therefore, because the mathematical statements are talking about numbers, therefore the mathematical statements can be talking about mathematical statements. And this way, self-reference is sneaking in to mathematics. We get a capacity for self-reference in mathematics. Okay, so one of the things that we could do is say, in the language of arithmetic, we can express the operation of Turing machines. Because what is a Turing machine? Well, the program is this finite list of these 5 tuples, right? A list of the state and reading information to the new state and what you should write and which direction you should go. So a Turing machine program is a list of those instructions, and all of that can be coded with a number. And the operation of the Turing machine on a tape, if we think about taking a snapshot of a Turing machine, what information about the machine do you need to know in order to, track the progress of it? But you need to know what program it's running. You need to know where the head is. You need to know the contents of the tape, of the finite part of the tape that's been changed so far. And so you can code all of that with a number, and then you can say whether this number is leading to this number on the very next step of operation, and so on. And so in this way, we arithmetize the operation of Turing machines into the language of arithmetic. Okay, so there is an issue, a difficult philosophical issue concerning the veracity of these translations. So, for example, if someone's writing a great novel, then it's not a criticism to say, look, that's not a novel, that's just a really long, boring sequence of zeros and ones. I mean, because the Gödel code, inside the computer is just this long, boring sequence of ones. That's to confuse the code with the thing that the code is representing. And so it's a kind of philosophical puzzle to determine exactly what do we mean when we say that this structure is represented by this code after the arithmetization process. So there's quite a lot that one can say about that. Okay, let me now turn and give a second proof of the first incompleteness theorem, which is a little more in line with Gödel's proof, and maybe is a proof that you may have heard of. Okay, so what I want to do is talk about what's called the fixed point lemma. Okay, maybe I'll write it on the board. So the fixed point lemma says that here's the fixed point. Fixed point lemma. And what it says is, in the language of arithmetic, for any formula with one free variable, there is a sentence psi, such that, say, our basic theory, maybe let's just take it as piano arithmetic. The piano axioms prove that psi is equivalent to phi of the Gödel code of psi. So these angle brackets on top is called the Gödel code. So that's the number that's representing the sentence psi. So both of these are assertions in the language of arithmetic. This one has a free variable. This is a sentence, which means it has no free variables. So this is the Gödel code of psi. And we're proving that psi is equivalent to phi of the code of psi. So let's talk a little about what that means. So it's basically the sentence psi is asserting phi holds of me. Yeah, this is self-reference. The fixed point lemma is self-reference because psi is making an assertion about its own code. Okay, and this lemma is incredible because it's saying that every property admits such self-referential assertions. Every arithmetic property allows for this kind of self-reference. So let me give the proof. It's not that hard to prove it, although the proof is completely mystifying, maybe. Okay, so this is the proof. So first I want to introduce a function, the substitution function, and it takes a code, the Gödel code of a formula with a free variable and a number, and gives you back the Gödel code of the formula that you would get by substituting that number into the formula, where by n underbar I mean 1 plus 1 plus and so on, n times. So that's a syntactically allowed expression in the language, and I want to put that into the variable of phi and take the Gödel code. So this is a primitive recursive function, and therefore it's representable in the language of arithmetic, and PA proves that it has all the properties that you want. Okay, So now I proved that using this sub function, I'm going to prove the fixed point lemma. And it goes like this. So let theta of x be phi of sub xx. Okay. So that's a formula that's got a free variable. And now let n be the Gödel code of theta of x. Okay. This is a formula, so it has a Gödel code. And I'm letting n be that Gödel code. And now let c be theta of n. Okay, I plug in n for the variable of x. Okay. And I think that's the c that's going to work. And let's see that. Well, theta of n is equivalent to phi of sub nn, because that's what theta of something is. But this n is the Gödel code of theta of x. So this is if and only if phi of sub theta, the code of theta of x, n. I'm only changing the first n to the code of theta of x. Okay. But the sub function takes its second argument and inserts it for a variable here. So this is the same thing, a logically equivalent to saying phi of the Gödel code of theta of n. But theta of n is c. So this is if and only if phi of the code of c. Okay, so we've proved that c is equivalent to phi of the code of c. Okay, that's the proof. It's maybe hard to see how someone would come up with a proof like this. It's, of course, one can follow each step easily. You can also see where this diagonalization is happening. So this diagonalization here, sub xx. Okay. So let's now use that fixed point lemma to prove the Gödel incompleteness theorem. So what I want to do is consider the sentence. I mean, we can express a lot of syntactic ideas in the language of arithmetic because of arithmetization. So we can say things like x is the code of an axiom of PA, or we can say x is the code of a theorem of PA, or x is the code of a provable statement. Or maybe we want to say x is not the code of a provable statement. Okay. So what if we find a fixed point for the following assertion? Okay, let me erase this fixed point. No. So we have a theory T, which is computably axiomatizable and true. And then we can formulate the predicate PRT of X, which is formulating the idea that X is the Gödel code of a provable statement in T. It's provable from T. Okay. And now I want to apply the fixed point lemma to get a sentence C, which is equivalent to not PRT of the code of C. Okay. So using the fixed point lemma, we can find such a sentence C, which is equivalent to any property we want about C, but I want to use this not PRT of C. And so C is asserting, sort of more colloquially, C is not provable. Using the fixed point lemma, there's a sentence that asserts of itself that it's not provable in T, or from T. Okay, so there's a sentence that says, I am not provable. And now let's think about what is the nature of that sentence. Maybe you're familiar with the liar paradox. That's the sentence that says, this sentence is not true. And the usual analysis of the liar paradox is that, well, look, the liar, the sentence that asserts its own falsity, can't be true because then it would have to be false, and it can't be false because then it would be true. And so it's this paradoxical statement. Maybe it's problematic to have such a statement at all. But the Gödel sentence, this one, that asserts its own unprovability, definitely is a perfectly legitimate mathematical statement. It's a statement in the language of arithmetic. It's about adding and multiplying numbers and whether there's a number such that something or other. And so, so So there's no question about whether the sentence exists or is meaningful. It's making a certain arithmetic assertion. And what it means is it's asserting that it itself is not provable. So it's something like the liar. And what is the sort of outcome of the liar paradox analysis that we get when we apply that analysis to the Gödel sentence? Well, let's just see. The Gödel sentence asserts its own non-provability. So if it were provable, right? So if we could prove the Gödel sentence, then we could prove that it was provable, right? And so it would be false. So we would be proving something false then, right? Because the Gödel sentence asserts its own non-provability. So if we could prove it, then we could also prove that we could prove it. But it's equivalent to its own non-provability. And so we would be proving the negation. So if we could prove it, we could also prove the negation. Okay, so that can't happen. So therefore, it must not be provable. But that's what it says. So we found a true statement that's not provable. The Gödel sentence cannot be provable. Therefore, it's true, because what it says is that it's not provable. Okay, so that's the proof of the first incompleteness theorem using the Gödel sentence. So the theorem can be stated like this. Every consistent computably axiomatizable theory of arithmetic admits true but unprovable statements. The Gödel sentence is true but not provable. Okay, and that really refutes the first part of the Hilbert program, because Hilbert wanted to find this even in the infinitary realm. He was willing to go to the infinitary realm. He wanted a complete theory. He wanted to write down a complete theory that would answer all the questions. But the incompleteness theorem says, look, you can't even do it in arithmetic. You can't even write down a theory that's going to prove all the true statements, because every computably axiomatizable theory, every consistent computably axiomatizable theory of arithmetic admits true but unprovable statements. Okay, so let's now turn to the second incompleteness theorem. So the second incompleteness theorem is a bit stronger. So it says that if you have a consistent computably axiomatizable theory extending Peano's axioms, then it does not prove its own consistency. So no such theory can prove its own consistency. Now, the consistency of a theory is a syntactic property of the theory, right? If I have a computable axiomatization of the theory, then I can write down in arithmetic what it means to have a proof from that theory, or to have a proof of a contradiction from that theory. And so this is subject to the process of arithmetization. So I can formulate the assertion that the theory is consistent as an expression in the language of arithmetic. And the point is that the theory will not prove that statement that it asserts that the theory itself is consistent. Okay, so the proof, this is a consequence of the first incompleteness theorem if you think about it in the right way. For the first incompleteness theorem, we proved that that if the theory T is consistent, then it doesn't prove the Gödel sentence. Yeah. But if we formalize that, right, then what we've really shown is the following. Let's see. So we have the theory T, and we found the Gödel sentence. So PA proves that that C is equivalent to its own unprovability, right? And the first incompleteness theorem says that if T is consistent, then T does not prove C. Yes. So another way of thinking about what this says is that really, if we formalize this in Peano arithmetic, PA proves that con T, that's the assertion that T is consistent, implies not PRT of C. Okay. So I'm trading the kind of meta-theoretic provability predicate for this arithmetized provability predicate. And so the proof is really about the interplay between the provability relation and the arithmetized version of it. One of them is in the meta theory, and one of them is in the object theory, right? This PRT of something is an object theoretic account of provability. And when I write the actual provability symbol, I'm operating in the meta theory. But the point is that we can formalize that argument we gave of the first incompleteness theorem inside arithmetic and prove in arithmetic that if the theory is consistent, then it doesn't prove its own. Then it doesn't prove the Gödel sentence. Okay, but this is equivalent to psi, right? So we've got con t implies psi. So t proves that con t implies psi. But t doesn't prove psi, so it can't prove con t, because if it proves con t, it would have to prove the Gödel sentence also. So that's the second incompleteness theorem. You can't prove con t, because then you would prove the Gödel sentence, but you don't prove the Gödel sentence. Okay. Now, when one gets into the details of the argument that I just described, of course, it's not possible in such a lecture to give all the details. But if you look in the book, there's much more detailed account. But I want to just highlight some of the principles that we're using there, namely. So these are called the Gödel-Loeb proof conditions. The Bernays, also Bernays, let's see, what is it? Hilbert, Bernays, Loeb derivability conditions. So D1 is the assertion that if you can prove something, then in PA you can prove that you can prove it. Okay. If something's actually provable, then it's provably provable. Okay. And D2 is the assertion that PA proves that if something is provable, then it's provably provable. Okay, so this one is sort of arithmetized version, really, of that one. And then D3 is the condition that piano arithmetic, if piano arithmetic proves that phi is provable, and it proves that phi implies psi is provable, then it proves that psi is provable. Okay, so this sort of scheme of assertions. Maybe I shouldn't use psi here because that's the Gödel I was using for the Gödel sentence. I'm not talking about the Gödel sentence. Let's just write sigma here. So it's like modus ponens inside the object theoretic provability predicate. Okay. So from these derivability conditions, then that's really all you need to know about the interplay between the meta-theoretic provability notion and the object theoretic provability notion in order to prove the second incompleteness theorem. Okay, so let me mention now another variation. So Gödel's theorem, the way I stated it, was that every computably axiomatizable consistent theory admits true but unprovable statements. But that doesn't imply that it's incomplete unless the theory was also true. Because, right, what we really want to know is that every computable consistent theory is incomplete. It would be a stronger result. Maybe it didn't prove that true statement, but it proves the negation if the theory itself wasn't true, right? So we get a slightly stronger result, which is known as the Gödel-Rosser theorem. So this is Rosser's formulation of the theorem. Gödel didn't need that the theory was true. He could get it was incomplete if he assumed this technical condition called omega consistency, which now is maybe not so important in light of Rosser's improvement of Gödel's theorem. So the way to think about it is that Rosser's formulation of the theorem is simply better than Gödel's, and the Gödel-Rosser theorem is the right theorem. Every consistent computably axiomatizable theory T, which extends PA, is incomplete. That's what the theory says. And he doesn't use the Gödel sentence, but a different sentence, which has become known as the Rosser sentence. So the Rosser sentence rho says it's a fixed point for the following property. Rho is equivalent to the assertion that for every proof of rho, there's a shorter proof of not rho. Okay. And when I say a shorter one, I mean one with a smaller Gödel code. Okay, not just fewer steps, but the coding is smaller. So Rho says, for any proof of me, there's a smaller proof of my negation. Okay, so let's think about that statement. Well, could it be provable? Well, if you proved it from a theory T, then you could prove that you could prove it using the derivability conditions, and that proof would have a certain Gödel number, and the theory, since it extends PA, knows exactly what all the smaller numbers are. So if you could prove it, then I mean, what it expresses is that for every proof of rho, there's a smaller proof of not rho. So therefore, one of those smaller numbers, if the statement were true, one of those smaller numbers would have to be a proof of not rho, but it can't be, because then you would be proving both rho and not rho. So but the theory was consistent. So regardless of whether it's true or not, the theory is consistent. And so it must be that none of those smaller numbers is a proof of not rho. And so therefore, the theory can't have proved rho, because it will also prove of each and every one of the smaller numbers that it's not a proof of not rho, and that's a contradiction. So T would have to be inconsistent. So T can't prove rho, and very similar reasoning shows it can't prove not rho either, because if it was proving not rho, then, well, what does not rho say? I mean, if you prove not rho, the negation of the Rosser sentence says that it's not the case that for every proof of rho, there's a smaller proof of not rho. But we have a proof of not rho right here, right, under the assumption that there was one. And so therefore, if there was any proof of rho at all, there would have to be smaller, but there must be one, in fact, because otherwise the statement rho would have been true, but we're proving not rho. And so one of those smaller numbers must be a proof of rho. And again, we're going to get the inconsistency of the theory. Okay, so that kind of reasoning, I'm sorry, it's probably terribly confusing. You can so easily get yourself tied up in knots with this kind of self-referential reasoning in the incompleteness theorem. And I probably said some wrong things already about it, because it's really easy to get confused about when you're making all these self-referential statements. Okay, let's turn now to Tarski's theorem. So Tarski proved a remarkable theorem which fits in with the incompleteness theorem, namely, Tarski proved that there's no definable predicate T of X, which holds exactly of the statements of the Gödel codes of true sentences. So let me state it like this. So the theorem is Tarski's theorem. So there is no definable in the language of arithmetic, predicate T of X, such that the natural numbers satisfy T of the code of phi, if and only if phi, for all sentences phi. Okay. T stands for true, right? So he's saying, look, you can't express what it means for X to be the code of a true sentence. You know, this is the scheme of what it would mean to have such a predicate, but there can't be any such predicate. This is an almost immediate consequence of the fixed point lemma, because if we had such a predicate T, we could just find a fixed point for not T. Yeah, so we would find a sentence that was asserting its own non-truth, but then it would be true if and only if it's not true. It would be exactly like the liar paradox, right? So, okay. So actually, Tarski proved a subtler version of the theorem, which is that there can't be a formula sort of whose satisfying instances fulfill the Tarski recursive definition of truth. So the sort of slogan form of this is that you cannot define truth. Truth is not arithmetically definable. Arithmetic truth is not arithmetically definable. And Raymond Smullyan has argued that much of the attention and fascination that accumulates around Gödel's theorems are actually more aptly directed to Tarski's theorem instead. Okay, and there's another sort of awkward issue. It's not, I guess not terribly awkward. Tarski is credited with defining truth. He's defined the satisfaction relation, I mean, the disquotational theory of truth. So Tarski defined truth, but he also proved that truth is not definable. And so it's sort of strange situation. Of course, both of those things are correct, understood in the right way. Let me now talk about Peppermints theories. So Peppermint highlights a certain aspect of the incompleteness theorem by which the consistency assertions made about a theory are really intentional as opposed to extensional, depending on the theory. So, so let's consider the following theory. I'm gonna enumerate the axioms of piano arithmetic, but I'm only gonna put the next one on the list if the theory that I get is consistent. Okay, so I only allow the axioms onto the list if the theory that they result in is consistent. And that's arithmetically describable, right? To be consistent theory is an arithmetically expressible property. So I've described a certain axiomatization. Let's call it PA star. So PA star, it's a subtheory of PA. PA star is just like PA, except I only put the next axiom on the list if the theory that I get by doing so is consistent. Okay. Now it's sort of trivial to prove that PA star is consistent because at every stage it was consistent because I didn't allow the axiom on, and I didn't allow any axiom on that would lead to inconsistency. So if it was inconsistent, then that axiom needed for that inconsistency wouldn't have been added. Okay, so it's very easy to show that PA star is consistent. And also PA star is identical to PA, in fact, because piano arithmetic proves of any given finite fragment of piano arithmetic that it is consistent. One can show. This is known as the reflection theorem. So PA proves any given finitely many axioms of PA are consistent. So in particular, it's true that they're consistent. And so all of the axioms of PA will in fact be added to PA star. So PA and PA star as theories extensionally are identical, and yet PA star proves con PA star. So we've identified a theory that proves its own consistency. So doesn't that contradict the second incompleteness theorem? Because the second incompleteness theorem was the assertion, right, that no computably axiomatized consistent theory proves its own consistency. But here we have this theory PA star that does prove its own consistency. And the resolution of this is that PA star is not computably axiomatizable, because whether or not a given sequence of axioms is consistent or not is not something that is computably decidable. That's an existential statement. Is there a proof of a contradiction? I can't computably answer that question because of the enchantings problem, the undecidability of the enchantings problem, and therefore PA star, I haven't described a computable axiomatization of PA star, even though it turns out to be the same theory as PA. So the point I'm trying to make is that the assertion that a theory is consistent is not just about the theory, it's about the way that you describe the theory in arithmetic. You know? Because con PA and con PA star are not equivalent, are not provably equivalent statements, even though they're talking about ultimately the same theory. We can't prove that they're talking about the same theory in PA, you know, even if it's true that they're the same theory. Okay, so that therefore there's a kind of measure of intentionality to these consistency assertions when you formalize them in the process of arithmetization. Okay, let's talk about the ubiquity of independence phenomenon, right? So the incompleteness theorem says, look, any given theory is going to admit true but unprovable statements, such as con PA is not provable in PA. So if we started with PA, we could go to the stronger theory, PA plus con PA. So we start with piano arithmetic as our base theory, but we can't prove con PA in it. So I could make the theory better by looking at PA plus con PA. This is a computably axiomatizable theory, which is consistent. And it doesn't prove its consistency. So I can make a stronger theory by adding the consistency assertion. So I make PA plus con PA, that's the same theory, plus con PA plus con PA. This is a strictly stronger theory because this consistency assertion is not provable in that theory itself. Okay, that's a computably axiomatizable consistent theory, and therefore it admits true but unprovable statements, for example, its own consistency assertion. And so again, I can say PA plus con PA plus con PA plus con PA. Okay, that's the same so far. Plus con of that whole thing. Yeah, if I take this whole thing and stick it in there. There's certain redundancy because, of course, con PA plus con PA implies con PA. So I didn't actually need to write this part. And this part is a consequence of the next also. So even here, I didn't need this axiom because it's a consequence of this one anyway. So one can simplify the statement. But the point is that one can iteratively add the consistency assertions and get stronger and stronger theories. There's a hierarchy of consistency strength. Okay, and it doesn't just go finitely many steps. You can go transfinite for any countable ordinal that you can describe in arithmetic. So omega squared plus 5 or whatever ordinal you want. You can talk about the iterated consistency theories that you get by adding consistency statements at each step. And they get strictly stronger, provably so. So one can iterate this transfinitely. So what Gödel really discovered was this kind of fundamental phenomenon of an underlying inherent transfinite tower of consistency strength looming above every theory. No matter what your theory is, if you can describe it by a computable accentization, there's going to be this tower of stronger and stronger theories in the consistency strength sort of towering over it. And one would maybe want, well, are there any natural examples of these sort of true but unprovable statements in that hierarchy? Because maybe, okay, you say, well, we can't prove the Gödel sentence, but the Gödel sentence is just this sentence that's all tied in knots with this self-reference. And maybe you're not too worried about not being able to prove that true statement. Okay, it's not such a natural statement to look at other than the fact that it's a true but unprovable statement, which is a very interesting thing about it, except that it's this weird statement, right? So we want natural examples of true but unprovable statements or independent statements. And maybe one of the best examples of this arises in set theory with the large cardinal hierarchy we're going to talk about next week. So we have these extremely natural principles of infinity, and they fit into this large cardinal hierarchy in such a way that any given existence assertion for one of the large cardinals is implying the consistency of all of the smaller ones. So the large cardinal hierarchy is exactly instantiating this tower of consistency strength that Gödel's theorem tells us must be there. So we found it in the large cardinal hierarchy. And those statements are not at all of this kind of syntactic self-referential nature, but rather express basic principles of infinite combinatorics. They're expressing the existence of extremely large infinities with certain features, and they happen to have this consistency tower relation. Okay, but then purely in arithmetic, one can also make examples. So let me show you one. Let's see, I think I'm going to skip over this reverse mathematics stuff. There's quite a bit more in the chapter. So let me mention, though, one of the most attractive of the arithmetic statements that's independent, and that's Goodstein's theorem. So start with any number you want. I'm gonna let's see, what do I start with in the book? 73. So, and then what you do with that number is you write it in complete base 2. So if I write this in base 2, let's see, this is 64 plus 8 plus 1, and 64 is, what is that, 2 to the, what is it, 2 to the 7 or 2 to the 8? No, what is it? It's what is 64? It's 2 to the 6th. 2 to the 6th plus 2 cubed plus 1. Okay, but complete base 2 means I write the exponents also in base 2. So 6 is 2 squared plus 2, and 3 is 2 plus 1. Okay, plus 1. So this is 73. In complete base 2, which means you write it as a sum of powers of 2 and the exponents also. Let's call that a sub 2. Okay. And now the Goodstein process is the following. So we make the number a sub 3 by replacing all of the 2's with 3's and then subtracting 1. So I'm going to get 3 to the 3 to the 3 plus 3 plus 3 to the 3 plus 1 plus 1 minus 1. Okay, so this subtracting 1 is going to cancel out this one here, and so ultimately I get 3 to the 3 to the 3 plus 3 plus 3 to the 3 plus 1. Okay, it's a gigantic number. I mean, 3 to the 3 to the 3 is what? 3 to the 3 is 27. This is 3 to the 30. Okay, it's an enormous number already. And then a sub 4 is you replace all the 3's with 4's and subtract 1. So then we get 4 to the 4 to the 4 plus 4 plus 4 to the 4 plus 1 minus 1. But I have to write this in complete base 4, so I can't have this minus 1. I need to break up this expression, yeah? And so it's going to be 4 to the 4 to the 4 plus 4. That's the first term, plus. Well, when you break up an expression like this, then you're going to get 3 times 4 to the 4 plus 3 times 4 to the 3 plus 3 times 4 squared plus 3 times 4 plus 3, right? If you think about the base 4, what happens in base 4 when you subtract 1, you get all 3's, right? Just like in base 10, when you subtract 1 from a big power of 10, you get all 9's. Okay, so, and so on. A5, replace all these 4's with 5's and so on. These numbers are getting enormous. And now the theorem, the first theorem, Goodstein's theorem says, no matter what you start with, no matter what number you start with, what positive energy you start with, there is a number n such that a sub n is equal to 0. You eventually hit 0. And that seems very strange because it seems like these numbers are getting bigger and bigger and bigger. But in fact, what happens is that you eventually, the base is catching up with the number, and then you're just subtracting 1 forever, I mean, for a long time until you get down to 0. Okay, so they don't keep getting bigger and bigger. You can sort of start to see a little bit about what's happening in this step from A3 to A4, because when I had to break up this expression now, you know, before I had 4 to the 4 plus 1, but now, now I don't have any, I don't have, you know, I've got these other ones with these 3's, and now these 3's are no longer going to be replaced with 5 and 6 and so on at the next stages. Only the 4's will. And so the number, although it's bigger, it's simpler with respect to a certain measure, you know, and the measure that's useful for the purpose of proving Goodstein's theorem is a countable ordinal representation. So whenever you have a number like this, you replace all the 2's with the ordinal omega, and you interpret it as a countable ordinal. So this would be omega to the omega to the omega plus omega to the omega plus 1 as an ordinal. And then the next one, this ordinal, is strictly smaller. Even though the number got bigger, the ordinal that you're associating to it, you can prove is strictly smaller. So the way you can prove Goodstein's theorem is you prove that those ordinals are descending. But there's no infinite descending sequence of ordinals. So therefore, you must hit 0. So the only way that can happen is if the number itself was 0. Okay, so that's Goodstein's theorem, which is a fantastic theorem because the theorem itself is surprising. But it packs a 1-2 punch because Kirby and Paris proved that Goodstein's theorem is not provable in piano arithmetic. So another way of thinking about this is the proof of Goodstein's theorem was using sort of infinitary ideas, these ordinals. So basically, it's a proof in set theory that you hit 0. But if you just want to stay inside arithmetic with the piano axioms, it's not strong enough to prove the theorem. So Goodstein's theorem, that fact that you hit 0 always, is a true but unprovable statement in piano's axioms. Okay, and there's other examples of natural statements that are true but unprovable. There aren't any really easy ones. I mean, they're all somewhat detailed because it's quite a significant criteria that one wants to find a true but unprovable statement. And so they're all quite complex statements, but there are ones that are more natural and less connected with the logic itself. Okay, let's see, I'm running out of time. Let me talk briefly about Loeb's theorem. So, okay, we have the liar sentence that says this sentence is not true. You know, this sentence is false. But there's also the truth teller sentence that says this sentence is true. Okay. There's the Gödel sentence, which says this sentence is not provable. And the analog of that one would be the Loeb sentence, which says this sentence is provable. Right? Now, oftentimes, when you're analyzing the liar sentence, right, the sort of usual analysis that one hears is, well, the liar sentence that asserts its own falsity can't be true because then it would be false, and it can't be false because then it would be true, and therefore it's sort of contradictory or paradoxical. And when you try to analyze the truth teller, the sentence that says this sentence is true, then the corresponding analysis says something like, well, if it's true, then it's true, and if it's false, then it's false. And sometimes people say, therefore, it can be either one. But that's just not right. That's just because you tried to give an argument and you didn't make a conclusion doesn't mean that it can be either one. That's just not a correct argument, right? It's a failed argument. If you said if it's true, then it's true, and if it's false, then it's false, then you haven't really argued for either one of those, and you still don't know whether it's true or false. And let me convince you that that's a right way of talking about the truth teller sentence, because the Loeb sentence, which asserts its own provability, if we tried to do the analog of the truth teller analysis, then you might say, well, if it's provable, then it's true. And if it's not provable, then it's false. And so it can be either one. You might be tempted to say it can be either one, that it would be independent. But that's wrong, because in fact, the Loeb sentence is provable. We can prove it. There's a proof of the Loeb sentence. And therefore, it's true that it's provable, because what it asserts is that it's provable, and in fact, it is provable. Okay, and that gives you reason to think that that naive analysis of the truth teller sentence maybe leaves something to be desired, because it didn't work with the Loeb sentence in arithmetic. Okay, I think I don't have time to give the proof of that. So let me just conclude by mentioning these sort of two uses of the word undecidable. We have the word undecidable. We talk about whether a decision problem is decidable or undecidable. Yeah, and that means the decision problem is decidable if there's a computable procedure that will answer correctly all instances of that problem, yes or no. And it's undecidable if there isn't such an algorithm. And then we also talk about whether a given statement is decided by a theory. In other words, whether the theory proves it or refutes it. Yeah, so we can say, for example, the continuum hypothesis is undecidable in Zermelo-Fraenkel set theory, because Zermelo-Fraenkel set theory doesn't prove the continuum hypothesis, and it doesn't prove the negation either. Okay, so those seem superficially like two totally different uses of the word undecidable, and so it's good to attend to this word and the fact that they have these different meanings. But in fact, one can say more, namely that those two uses of undecidability are nevertheless deeply connected, and so let me convince you of that. Suppose you have an undecidable decision problem. Okay, so you have some problem, let's call it capital A, and there's no computable procedure to determine in general whether a given number is in A or not. Okay, so it's undecidable in that computable sense. Then I claim there must be, for any theory of arithmetic, for any true theory of arithmetic, there must be instances of your problem that the theory cannot decide, cannot prove. It doesn't prove them or refute them. And the reason is that if your theory settled all instances of that decision problem, then you would have been able to decide computably the problem originally, because you would just look for proofs, right? This is the same idea. So you look, given, if the theory did settle all instances of the decision problem, then given any number n, and you want to know is n in the problem, is the answer yes or no, then you just look for proofs. And either the theory is going to prove that the answer is yes, or the theory is going to prove that the answer is no, and you just wait. And you're going to get one of those answers, and then you say yes or no accordingly. And so if all instances of the decision problem were settled by the theory, then that would be a decision problem for the original problem. But you said that the decision problem was not decidable, so there can't be any such algorithm. Therefore, there must be specific numbers so that the theory does not prove whether or not that number fulfills the decision problem or not. Okay, I guess that's it for today. And so we can have discussion if people have any questions. So let me just maximize this. So please feel free to unmute. Okay, somebody asked, how do we define the provability predicate? So this is using the idea of arithmetization. So essentially any syntactic property can be formalized in the language of arithmetic. So what we need is to develop the details of the Gödel coding. I mean, it's something like being a computer scientist designing the circuitry inside your computer so that with the zeros and ones that are representing the ASCII codes and so on, it's able somehow to handle your Word document when you type in. So the process of arithmetization is analogous to that process of designing the computer circuitry so that it's implementing the sort of high-level ideas at the level of the zeros and ones that are actually representing the codes. And so one needs to develop this theory, and I didn't do really any of that in this lecture. It's traditional, actually, when proving the incompleteness theorem, sometimes people, I think it used to be much more true than it is now, people would spend an inordinate amount of time on the details of the coding. But my view is that those details are almost completely uninteresting and arbitrary. There's a lot of different ways to carry it out, and none of it is surprising in the slightest because of this fact that we're all so familiar with the basic idea of arithmetization. We already know that in principle, when you type on your computer, that the stuff can be represented inside the computer with zeros and ones. And so there's absolutely nothing surprising about any of those details. And it's just not necessary to carry out all those details. It adds essentially no convincing aspect to the proof as far as I'm concerned. And so that's why I don't tend to do a lot of it. But it is possible in principle to just say more about exactly how you're coding formulas and how you're splicing substitution instances in, and how you're handling the parse tree and so on. And it's definitely possible to give all the details of that. The question is whether doing so adds any insight to understanding the proof. And I think it adds very little, although of course, to have a rigorous proof, one should, explain exactly how that coding is working. So in a 1 hour lecture, it wasn't really possible. So I apologize for that. Let's see. Do you please say, what do you mean by a proof of the first incompleteness theorem via definability? Right. So what I was referring to there was Tarski's theorem. So Tarski proved that truth is not definable. And it's an immediate consequence of Tarski's theorem that the first incompleteness theorem holds, because right. So that's all I meant. Okay. Any other questions? Feel free to unmute if you want to ask questions.
I have a question.
Sure, Aaron, go ahead.
So you said at the beginning of the lesson you were describing this world where Hilbert's program fails, and you said that mathematicians might be like trying to add axioms or discussing axioms, and we don't really know what all the axioms are, maybe. And then you also said, then you showed that Gödel's incompleteness theorem says that Hilbert's program is definitely not true. So do you think that it happens now in math, that mathematicians are discussing axioms or adding new axioms?
Yeah, I think absolutely. That's part of what's going on in set theory and the philosophy of set theory, for example. The incompleteness theorem says we can't ever sort of complete the task of axiomatizing the fundamental truths of mathematics. And therefore, all of our axiomatizations are necessarily unfinished. And we must have conversations or arguments about, what the new axioms are to be, and on what basis are those decisions to be made. And that's what we see playing out in set theory, in my opinion, where we have the Zermelo-Fraenkel axioms, or maybe with the axiom of choice and the large cardinal hierarchy. Okay, those theories are all getting stronger and stronger, but none of them is complete. And so there's always still open questions about whether this principle or that principle should be added, and people maybe make arguments. And what is the criteria? For example, should we consider the fruitfulness of a new axiom as an advantage? Or what if we have a principle that's very fruitful, but we don't have any intuitive reason to think that it's true? Should that count as an axiom? Is that a good enough principle to add it as an axiom? We're going to talk about this more next week, but that's sort of what I was referring to. And we see it playing out, as I mentioned, with the continuum hypothesis. For example, there's people who think that the continuum hypothesis should be added the negation as an axiom, or the non-negated form of it should be added as an axiom, or that neither one, or and what's the criteria for deciding that? It's not a mathematical criteria. Basically, it has to be a philosophical one, precisely because we can't prove or refute these statements. And so the decision about whether to add it or not, and what does it mean to add an axiom anyways? Because of course, if you say, consider the case of geometry, right? We have Euclidean geometry and non-Euclidean geometry. And well, some days I do Euclidean geometry, and some days I do non-Euclidean geometry. And so what does it mean to add the axiom? Have I added the Euclidean axiom? Because I was using it in a certain proof, but maybe the next day I'm going to use a different theory. And so did I take away the axiom again? Or if I prove a theorem in set theory and it's using the continuum hypothesis, and then the next day I want to use, say, Martin's axiom with the negation of the continuum hypothesis, have I taken the axiom away? No. So what does it mean to add the axiom in the first place? Yeah. And what are the criteria by which we add axioms? And these are all extremely rich philosophical questions to consider. Any other comments, discussion, questions? Okay, in that case, I'll see you all next week. We have set theory next week and the philosophy of set theory, so I'll be talking all about that next week. So see you all then. Bye.
Bye. Thank you.